Hi everyone, my name's Priyan. I'm an engineer and a DevRel at Arize. And today I'll be talking about how you guys can build self-improving agents through prompt learning. So let's take a look at this tweet from Andrej Karpathy, who many of you guys probably know to be one of the brightest minds and influences in AI and LLMs. So he said, we're missing at least one major paradigm for LLM learning, and he calls it system prompt learning. He says that while pre-training is for training some LLMs to have some corpus of knowledge, fine-tuning is for pushing LLMs to have some habitual behavior, and both of these involve a change in parameters, but a lot of human learning feels like more of a change in the system prompt. So as a human, you encounter a problem, figure something out, and then remember something for the next time and sort of edit your mental system prompt. And so he feels like editing your system prompt is kind of like adding to like your memory and adding some like problem-solving strategies or like approaches to however you make decisions in life. And he goes so far to say that LLMs, like without dynamic system prompts, feel like the guy in Memento, except we haven't given them their scratch pad yet. So if you guys haven't seen Memento, the crux of the story is that the main character, Leonard, literally can't remember what happened in his life 10 minutes ago. And so he continuously lives his life making new decisions with the same system prompt because he can't improve upon his decision-making and edit his system prompt because he can't remember his past decisions. And so he ends up using a scratch pad to write things down or write stuff down on his body, like you can see in the photo. And so this sort of becomes his new dynamic system prompt. And so Karpathy is going so far to say that LLMs without dynamic system prompts feel like Leonard from Memento, who can't remember what happened in his life 10 minutes ago. The system prompts are key to building effective language models. In case you guys missed it, Claude's system prompt was leaked a couple months ago, and it is 24,000 tokens long, or 18,000 words long. I mean, it has been like meticulously shaped into what it is now, and without a system prompt, Claude simply wouldn't be Claude. Now, unlike Anthropic, you guys probably don't have hundreds or thousands of employees watching your LLM answer queries and editing its system prompt. You guys probably don't have the time or the proper tools or knowledge to manually improve and iterate on your system prompts, which means that if you want to improve your LLM applications, you have to automate the improvement of your system prompts. And so in this push towards autonomous prompt optimization and allowing your LLMs to self-improve through their prompts, we introduce prompt learning. Prompt learning is inspired a lot by reinforcement learning. RL models are trained to pick an action based on a current state, from which you generate some scalar reward for the model or some sort of like score based on the action that the model took. And then you use algorithms like gradient descent or proximal policy optimization or Q-learning to update the weights or parameters of the model based on these rewards. So let's say that you were trying to make like a student smarter. So the RL model would be like the student's brain. The student would take an exam, that would be like the action taken by the model. Then you would have the score for the exam, that would be sort of like your reward function. And then let's assume that the student has some like gradient descent algorithm built in. So you can update the actual, like you can update the student's brain and like the neurons and weights in the student's brain based on this scalar reward using this algorithm. Now the problem is that updating weights directly is a difficult task. Prompts allow us to update or improve the model and update weights using text, which is what makes LLM so powerful. Prompts turn into tokens, which turn into embeddings, which then update the weights of a model. And so we're going to use a different algorithm called metaprompting so that we can improve the prompts of the model instead of the weights. So metaprompting is using an LLM to improve your prompts. It's the basic idea of just feeding your current prompt into an LLM and asking it to improve it. And so for our analogy, we're still trying to make the student smarter. So the student is like now an agent, and our student is going to take an exam. That's the output of the agent. We still have some score and some score generated from some function, so that's the exam score. And so now with our metaprompting algorithm, we're going to feed this student's exam score to a teacher, which is like our metaprompt LLM, and we're going to ask it to improve upon the prompt to a student or the prompt to the agent or like the homework or like lessons or homework assignments for the student. And so that's sort of serving as a prompt in this analogy. But there's a big problem in this loop, and it's that you can see that the teacher was only given the score of the students or this scalar reward. They don't know why the student answers some questions wrong, where the student needs to study more or improve, what types of problems the student struggles with most, and how the teacher can adjust his or her lessons and homework assignments accordingly. he or she only knows that the student got a score of like 75%. And so how can the teacher make better lessons or homework assignments or a better prompt for the agent with just this scalar reward, just a score, instead of actually having some analysis into the outputs from the LLM or like the exam outputs from the student? And so the question we're asking at a higher level is, how does the Metaprompt LLM know how to improve the prompt if all it's given is like the scalar reward or the scalar score of the output? It doesn't actually have analysis into where the prompt succeeds, where it goes wrong, why some outputs are wrong, the different nuances of the LLM outputs. A simple scalar reward simply provides very low information to a metaprompt. And so building better metaprompting with this type of feedback is prompt learning. Instead of the teacher just having some exam score of the student, let's allow the teacher to gather feedback on the exam. So like which answers were wrong, why answers were wrong, where the student needs to study or improve. And so at a higher level, this teacher doing analysis becomes an LLM doing evals and analyzing the agent's outputs for whatever information we think could be useful for the metaprompt. We can use an LLM to generate explanations for why certain outputs of the agent were correct or incorrect. We can even ask an LLM why it thinks the prompt failed for this specific output. And so this is just much richer information that we can feed into the Metaprompt LLM to succeed in building a better prompt. And actually, if we go back to Karpathy's tweet, you see in the last sentence of his tweet, he says, note that this paradigm is also significantly more powerful and data efficient because a knowledge-guided review stage is a significantly higher dimensional feedback channel than a reward scalar. So here's another way to look at this. Traditional prompt optimization is formulated like an ML problem. So you have some data, then you have a prompt, and you know that when you run your prompt on your data, you produce some outputs with some prediction labels. And the goal is to sort of maximize your prediction labels by sort of optimizing your prompt. And so we're modeling the prompt as this like box of numbers that we need to improve. Now, unfortunately, this is a difficult task given that prompts are built of text. It's hard to generate better natural language prompts through programmatic algorithms. And it's also hard to generate better prompts without analyzing the outputs for more than just their labels. So prompt learning lets you use LLM as judge evals, or asking LLMs to analyze your outputs. You can pass in human instructions or human evaluations as well to sort of get some more manual tuning of the prompt. And then this gets fed into a Metaprompt LLM, which uses all this information and all these explanations and evals to generate a new optimized prompt. So instead of treating the prompt as like this like box of numbers, you instead take it for what it is, text. You're going to use an LLM in your Metaprompt to generate a better prompt, since LLMs are good at handling text. And the context you provide to the LLM to generate a new prompt are eval explanations, which are also text, not numbers or metrics or scalar rewards. Actually, one time we were testing prompt learning on a classification example, so all the classes were passed into the prompt, and we asked it to classify. And when we passed in the whole prompt to be optimized, the optimizer accidentally changed like this one character in one of the classes in the prompt, and that actually led to a lot of issues in the downstream system because the system was expecting these like specific class names, and the LLM changed like the actual like name of the class. And so this told us that we shouldn't treat prompt optimization as this black box problem where you pass in the entire prompt and ask it to be optimized. It should be treated as like editing a body of text. You have some parts of the text that work well, right? Like the class names, you want to keep those there. There's some parts of the text that you want to improve or add upon. So that can be like explanations or instructions on how the prompt can be improved. And so this is just a better way of improving your prompts and like treating them as bodies of text because that's what they are. So there's many key benefits to prompt learning. We've got big boosts in accuracy for LLMs and also just strong, reliable prompts to the human eye. So this is something I'll show you guys in the next few slides. There's also high data efficiency, as you only need a few data points for good optimization. RL or programmatic optimizers like DSPy often require large data sets because they use scalar rewards. And so by using text feedback, even a few bad outputs or evals can allow a Metaprompt LLM to figure out what's going on and to figure out how to improve the prompt. Prompt learning also has really good transparency because the inputs and the outputs to the Metaprompt are text. So you can see exactly what's going into the Metaprompt, why the prompt is being improved in a certain way, how it's being improved. Also, the feedback that's given is in the form of evals, which are also text. So you can read these and you have like explanations for why the outputs that are generated by an LLM using your current prompt are correct or wrong. And this is something you can't do with reinforcement learning or programmatic optimizers. And so now I'll be moving on to showing you guys our testing. So we benchmarked on a few data sets for some insights into how prompt learning performs in a variety of tasks. In our benchmarks, we compare against Simba, which is a powerful optimizer from DSPy. We're actually aiming to get prompt learning into DSPy, but for now we compare it against DSPy Simba because it's the best prompt optimizer that we know that exists outside of us. So the first benchmark we built was for instruction learning. So testing whether prompt learning can improve an LLM's ability to learn like an instruction set or a rule set. So we tasked an LLM with generating web pages in JSON format based on some input. We had a set of rules. So for example, like always return valid JSON. Forms must include a method and a target endpoint. And the evals we provide to the meta prompt were explanations. So like explanations explaining why JSON outputs were correct or wrong. We also gave it a list of the rules that were failing. So instead of just a metric that says, oh, 60% of the rules passed, we actually gave it the list of rules that were failing so it can figure out how to improve the prompt. And we also passed in some suggestions from an LLM for how to improve the prompt just based on this specific output. And so we started off with a prompt that resulted in web pages that didn't follow any of the rules at all. And in just one loop, we see high accuracies like 84% or 66% based on the number of rules that we are checking. And in just 5 loops, we see even higher accuracies. And so what this shows is that prompt learning allows LLMs to learn new rules, up to even like 50 or 100 rules when it didn't know any of them in the first place. And so in the table, you can see that DSPy remains at 0% across all rule set sizes. And this is because DSPy fails to improve here because it has no access to the rule set. It only knows that the JSON outputs fail with some like sort of percentage or accuracy, but it doesn't know why they fail because there's no LLM evals to explain the weaknesses and the mistakes. So without that feedback, DSPy can't infer or learn the missing rules, so accuracy stays at 0. And this highlights a key advantage of prompt learning, which is when success depends on specific information, prompt learning can use evals to capture that information and inject it into the prompt, and inject those rules or instructions into the prompt, which is something DSPy simply can't do. And so back to Karpathy's point, this is how humans learn. We make a mistake, we have a teacher that tells us how to improve, and then we grasp this new idea. So in the next benchmark, we built this benchmark upon which we expected DSPy to actually perform well, and we compared prompt learning against it. And so we made a classification benchmark to test if DSPy and prompt learning can improve classification accuracy. We have a data set of support queries. So for example, my CC on file died, how fix? And we classify these. The LLM is prompted to classify these queries. And so the last one would be payment method update. We have some other classes like account creation, password reset. There's about 30 total classes. And so here, there's no rule set to be learned, as the classes we chose are pretty standard, and LLM already has the knowledge of what these classes should mean. So this is like fair for DSPy. There are 3 types of LLM evals that we fed into the Metaprompt LLM to improve the prompt. So we fed, just like the last benchmark, we fed an explanation, so why this specific output was correct or why it was wrong. We also asked an LLM to generate a reason for why the confusion may have occurred. And we also asked another evaluator LLM to extract the exact phrase that should tell our LLM that this query belongs in its correct class. And so you can just imagine that this is much richer information than just the correct versus incorrect or some sort of score. Like, we're actually seeing why some outputs are wrong, and a Metaprompt LLM is able to take this analysis and generate a new prompt much better. So our results show that on average, we had about a 17% increase in classification accuracy from about 54% to 71%. And DSPy Simba has very similar results, also reaching about 71% accuracy in its second loop. Simba's, so let's actually look at the prompts itself. I think these are like 2 very different optimization techniques, and they generate 2 very different prompts. So it could be useful for us to look at the actual prompts. So this is the base prompt that we started off with. We just passed in like the classes, and then we asked it to classify the query. So this is the base prompt. There's like no optimization done yet. This is the prompt generated by Simba. So you can see it's like, it also passes in the classes, and it asks it to classify, but it adds this one special rule, which reads, if the model receives a query that includes terms like cancel mid-month or partial money back, It should focus on identifying the context related to service terms rather than financial transactions, and specifies a little bit more about this specific difference in these two classes. And this is a very this is like a very efficient way to improve upon the prompt and increase the accuracy in the data set. It's finding this one special rule that the data set shows is like causing a lot of issues and incorrect outputs, and so it's adding that. Now, if we look at the prompt generated by prompt learning, you can see that this is like a more full fleshed out prompt, and it works a lot well for general cases, for like when you have inputs or queries that don't actually exist in your data set, but are more like general cases. And so metaprompting is able to sort of anticipate that and build a better generic prompt. You can see that we pass in some general rules. For example, this rule right here, which says number 2, it says, choose the most specific class that solves the user's main problem. Prefer the child over the parent. So for example, like, let's say we have 2 classes, login issues and 2FA. 2FA falls into like this like category of login issues, but let's say that the support query matches 2FA more. This prompt is essentially telling the LLM to pick 2FA over login issues. So this is like a very like generic, strong rule that will work for like all types of queries that are passed in, not just like specific classes. We also have some common decision points that it's identified in the data set. So like some specific keywords or like things in queries that point it towards specific classes. And if you see here, we also have some few-shot guidance. So we didn't instruct the metaprompter to add like few-shot learning into the prompt. It sort of did this on its own accord. And so this shows like the power of metaprompting and prompt learning, as it gives the LLM the ability to think on its own and figure out how to improve a prompt based on some eval explanations. So another benchmark we did was Big Bench Hard. So Big Bench Hard is a popular benchmark of tests that are deemed to be difficult for LLMs. And so we wanted to see if prompt learning could make LLMs better at tasks that LLMs are not supposed to be pretty good at. And so most of the time, BBH is reported as a single average, but I think the per task view gives much more information here. And so we saw that for some of the tasks, we saw like huge improvements in accuracy. Like you can see at the top, we have one of the sort of benchmarks in Big Bench Hard went from 0% accuracy to 0.8. And this is a really strong improvement. We see some other strong improvements like 38%, 38%, 30%, 10%. And so we also have some where there's not a big improvement or like a very small like actual decrease in accuracy. And these are the tasks where essentially like Big Bench Hard is a set of benchmarks that are supposed to be very difficult for LLMs. And so while prompt learning was able to do really well in some of them, which is a really powerful thing, the fact that it was able to improve accuracy for some benchmarks, which are like supposed to be very difficult for LLMs, is really strong. But it wasn't able to do them for all of them. And so now I'm going to give you guys a demo of prompt learning, specifically for the JSON web page generation data set. And so we're going to look at how prompt learning improves accuracy for JSON web page generation. So the first thing you're going to want to do is go to app.arize.com so you can see your Arize platform. You're going to click this data sets and experiments. And the first thing you want to do is you want to upload your data set. So your data set contains like your inputs or your queries, and essentially, like you want to run your prompt on your inputs and queries through an LLM, right? So you can experiment with like a base prompt and then optimize it and see how better prompts do. So you're going to want to upload your data set. So this is my data set right here. You can see that we have the inputs here. For example, create a web page with a navigation bar containing home, about, et cetera, et cetera. So this is the inputs we're going to pass in. So now you want to try out some base prompt. You have some idea for some initial prompt that you like want to see, and you want to see how it works so far. So you're going to initialize an experiment so you can experiment with your base prompt. Go to the prompt playground. Now let's start off with a base prompt. All right, so this is the prompt we're going to start off with. It's very simple. Just generate a JSON web page for the following input. And the first thing we're going to want to do is save this prompt. So I'm going to save it as JSON generation demo. And so basically what this experiment does is it's going to run this prompt on the inputs. And if you remember correctly, we want to also evaluate these outputs. We want to see how our current prompt is doing. We want to see if it's generating correct outputs. And if you remember correctly, the way we did this was through a set of rules. So we're checking if our outputs follow this defined set of rules. So if we go to this evaluators right here, we can look at this evaluator I've defined. which is an LLM evaluator. So we're passing in a prompt, and it's going to evaluate the outputs. So you can see here we pass in the input and the output that's generated based on the prompt. And then we pass in this set of rules that we wanted to sort of evaluate the output based on these like JSON rules. And another thing is that, remember, we're passing in this rich textual feedback, not just like this label for correct or incorrect or some score. So we're going to include an explanation, so a brief explanation for why the JSON web page is correct or incorrect. And also we're going to pass in an annotation, so like a description of what knowledge the prompt or the model may be lacking in order to generate like correct JSON web pages. And so this is all the feedback that we're going to pass in into the optimizer so that it can generate a new prompt. That's why we're generating it for each of our outputs using like our application prompt. So then you can press run over here to run the experiment. In the interest of time, I've already run that experiment. So if we go back to our data set and go to this experiments tab, you can see that experiment, the first experiment, and you can see it has 0% accuracy. So this is concerning. This means that our base prompt, when we ran it on our outputs, the outputs that were generated, like none of them satisfied the rule set. We had 0% accuracy, meaning that none of the outputs met any of the rules. And so what do you want to do after this? You want to optimize your prompt, right? So you can go to evals and tasks. You can initialize a new task for prompt optimization. You can call it anything. We're going to select a prompt to optimize, so we can select our prompt. You can see we have that prompt here. We want to choose a data set to optimize this prompt over, so we're going to pick our data set. Now you want to tell the optimizer which columns in your data set are the outputs, which columns in your data sets are the feedback to optimize the prompt, right? So you're going to pass in, or you're going to tell it which is the output column, and you're also going to pass in that text feedback to help it improve the prompt. So we have like correctness. We also have that explanation for why the output was correct or incorrect. We also have an annotation for how to sort of improve the prompt based on this. And so after that, you can click Create and Run Optimizer to run this optimization task. And so also in the interest of time, I've already run this optimization task. If we go back to the prompt hub, essentially this is where you can see all your prompts and all versions of your prompts. So this is the prompt I generated. We didn't do this in real time. This is the prompt that I had optimized beforehand for this presentation. So you can see that we start off with a base version, which is just generate JSON web page. This is our initial version. And then it gets better and better over these versions. Finally, you have this fleshed out prompt here where we're passing in some rules and instructions and just telling an LLM, giving an LLM a better idea for how to generate JSON web pages. And so now that you have your new optimized prompt, you want to verify whether this prompt is good or not. So you're going to run another experiment on your data set and see how well this does. So you're going to go back to data sets and experiments, go back to your data set, do a new experiment. We're going to pass in our prompt here. So we're going to go to our prompt, and we're going to click the newest version, so version 4. This is our most optimized version. Then you can run this task with the same evaluator. And so if we look at how that experiment performed, we can see that it had 67% accuracy. So through prompt learning optimization, we were able to get 67% better accuracy when it started off with 0. In the beginning, it couldn't understand, it couldn't produce outputs that followed any of the rules that we had defined. But after running our prompt learning optimizer, we're able to see like 67% accuracy. All right, so that's all for my presentation. You can check out prompt learning on our GitHub organization just by searching for prompt learning. You can also check out Arize, which is the platform I just demoed. You can do a lot of different things like generate traces, collect data for your LLM applications, evaluate your LLM applications, or improve your prompts like I just showed you. And you should also check out Phoenix, which is our open source alternative to Arize. Thank you.
Hey everyone, thanks Priyan for the presentation, and it was wonderful to learn about the prompt, meta-prompting and prompt improvement. So myself, Ankit, I'm from Turing, and today I'm going to talk about RL GYMS, the reinforcement learning environment that we have been building. A little about Turing, we use humans to make AI better, and we use AI to make humans better. So that's the loop we work on. We have 2 business lines. One, we have AGI advancement, which actually helps frontier models to train the model through the data that we provide and ship. And the second is the Turing intelligence, which actually we partner with the Fortune 500 companies, enterprises, and different SMBs as well, where we actually try and implement agents to improve some of the human workflows that these companies do. A little bit about me. Prior to Turing, I was at eBay, Walmart, and different marketplaces, worked in e-commerce, supply chain, run through different distributed systems, scale that from 0 to 1 to really scaling it to millions of orders, order processing, delivering it to the customers through last mile delivery. At Turing, my role has been building the product to scale the 4 million plus vetted developers and talent and the frontier talent that we have, along with now focusing on building RL Gym's product, which will help us providing the data sets which is the need of the hour for improving fine-tuning the models. With that, let's have a quick intro about RL Gyms and how we saw at Turing the evolution of these LLMs. Earlier, we used to have like one shot, and now you saw the prompt has been so well written, and now it has to be improved to improve the model. Second, we now expect models to actually not only just return the output that you need, but also to think, plan, and iterate on the mistakes that it has done. So along this journey, we saw initially last year and before that, a lot of data was we needed a lot of human-generated fine-tuning data for like supervised fine-tuning. But now what we see is like that has some challenges, and based on some of the research papers that's out this year, we have seen some challenges in scalability and what it could improve on. So for that, we have been seeing some challenges in terms of the scale at which we need this data. Also, we needed, it's costly to achieve like the frontier talent, and you have to generate so much SFT fine-tuned data. And that's why we have been focusing a lot on the reinforcement learning, where we are building some scalable product which will help us to provide this data and help the model to learn from these environment, real use cases, and we can iterate on, rather than just providing a supervised fine-tuning to the model improvement. And that's why we have been building RL Gyms. What is RL Gym? I think that's not a fancy term, but in a nutshell, it's an environment where we can actually test our agents, evaluate your model, where how is it performing in different scenarios. Two, it's a complete state. Like you get like a complete state of what environment you want to test your models, your agents, and so on and so forth. So it's a controlled environment where you can actually test out your agents rather than deploying it to the world and like you have so much feedback from the humans. Rather, you have this in a controlled environment where you can deploy these agents and learn from the trajectories. Third, it's a combination of scenarios and the prompts, like the real use cases where you would see how we can actually build it out with like a human experts that we have. And this is where we actually use a lot of human talent to curate these scenarios and so on and so forth. Last but not least, we have verifiers. So it has to be scalable. And to make this scalable, we want to make sure that it is able to continuously run and provide a deterministic output from the model. So we have verifiers that are automatically running. So think about like you can use this environment, you can checkpoint one of your model and see how it is performing around in this benchmark and evaluate it. And then moving forward, you can keep improving through the trajectories that we provide you as part of the data. And then you can see the improvement and keep testing. So you build it once, test it out multiple times along the way. Now, we provide two types of RL Gym. Your model might need the UI-based, where your model needs to perform some actions, your agents need to perform some actions on the UI, and there could be a non-UI way of interacting with the backend. Maybe some of you guys are engineers in the backend world, you have the APIs, and you can interact via that way through the workflows. So we provide both of these environments. We have built hundreds of the UI gyms, and we have built thousands of non-UI gyms that we support. As I said, in a nutshell, RL Gym has 4 big components. One is the environment. It's a controlled environment, sandbox environment for you to play around. We provide all the functionalities, or at least to an extent, the real functionalities which an environment should have. Second, it has the database and everything, all the state within it. So we provide all the seed data. You can bring in your own seed data, and you can set up this environment how you would want it to be. 2, we have scenarios. We have human experts who curate this. If you have a finance need, if you have a legal, accounting, you have retail, you have a bunch of different experience. We provide humans who curate these prompts. We use a lot of synthetic data as well to help us scale this out, but keeping the quality, which is our key focus on that front. As I said, this has to be automated. So we need to make this verifier so that you can keep checkpointing your model state and see where it is. You build it once, you test it out, you run it, and you improve your model through the fine-tuning data, and then you keep testing and keep iterating on the numbers that you have to move on. Last but not least, we provide this as a complete solution package in a gym environment, as you can think of. It will be deployed as a Docker image if that's what you're looking at. You can integrate in your existing harness that you have, or we provide you harness depending upon different mechanisms. But think about, you spin up, you bring up your Docker container, and here you go to run it in your environment if you need to be. So we want to meet you where you are. If you are already running some of this harnesses, we can provide you these Docker images which you can integrate in your system. As I said, we have seen a lot of interest in this space, and this is just a very small subset of, as we are getting to understand these models, these agents need to perform real-world tasks. We have been focusing into 2 different areas as a consumer. We have various areas like food and locals, travel, so on and so forth. We have mimicked a lot of these environments, if you can think of, into our gyms. So all you have to do is to select these environments, the ones that you care about, bring it up in a Docker container, and here you have the environment to play around your agent against. Similarly, we have seen a lot of interest on the enterprise side. Softwares, your day-to-day workflows, like from a sales and marketing workflows, we have experts who actually curate these prompts and verifiers. So you get these environments. Along with it, you get these scenarios, which are highly curated data, and you can run it multiple times as you checkpoint your model against some benchmark improvement in that space. And this is not just one tool. You can pick and choose your workflow. It can be cross-tools integration that you would need. So let me just quickly go through this animation. Yeah, so as you can see, there was thousands of gyms that we have provided. That was a sneak peek of few examples that we have seen our customers really looking for. But you can fundamentally think about the industry you're part of. You're building agents. You have the function, whether it's marketing, sales, different functions. Within each function, you have different roles, whether it's a CEO, CFO, or whether it's a junior engineer. They have different workflows in their day of a life. And then you have different scenarios that they want to, it's more like, what do you do in a day of a life? And then you can see those workflows that you could automate. So we see this as an intersection of these. And through this, you can definitely think about a lot of scenarios that we need to build. And we can test your model. And it's something, we're not trying to fine-tune a model by a supervised fine-tuning. We provide a lot of scenarios in the gym. You have verifiers, which can become your reward function that can be further included. With that, we go through this through a product way. The main challenge that we have seen is, like, how do you scale to thousands of gyms? How do you scale to so many verifiers? How do you build so many prompts and verifiers? Along with it, we cannot do it ourselves. We need some humans. And at times, we partner with various of the companies who actually try and integrate the environment they have. So we build it as a product. Here you can see we build, like Turing provides an RL gym product. As I went through it, it has the gym. You can bring in your own MCP server, or we have a lot of MCP servers that we bring it out of the box into the system. You have scenarios. You can build the database. You can bring in your initial seed data if some of the data that you have and you want to bring in to build your own scenarios. We provide you an API where you can actually hook your seed data. You can iterate on it. You can keep interacting with this environment. Similarly, we provide you a way to go through prompts. So you build your scenarios as complex as you want, and you can have a way to write a verifier for it. And the verifier can be, for each step you can have on a verifier, you can have an end result verifier as well to help your model on that front. So let me just quickly walk you through. This is how it looks like. This is a very small demo screen. You have a bunch of gym servers. These are behind the scenes MCP servers. You have tools defined. Think about like a Jira. You have like almost 400 APIs behind the scenes defined. All you do is register your server to our platform. You have a bunch of databases you could provide. You can create, you can clone. We provide some initial seed data. This is very highly curated initial seed data that you can take out of the box, but system provides you, a platform provides you to integrate and add your own data as well. As I said, next is the scenarios, human curated. We also use a lot of learnings to improve on our scenarios, and these are the data that we actually have trajectories built on the system, and we share that for fine-tuning data. Last but not least is the verifiers. These are sometimes as simple as a SQL query that you can have on the database, or it can be an LLM as a judge to finally help reward your model through that way. In this platform, as I said, we provide you a harness. If you have your own harness that you run it against your models in your iterative development of your model fine-tuning, we can provide you a way to integrate with your harness, or we can also provide a harness that we can keep checkpointing your model improvement there. You can also look at how we provide not only for your model, you can bring your own model and we can integrate it, but also we run it against frontier models to provide you a benchmark report in terms of how your model performs versus as compared to other in the frontier, right? That's all from my side. This is how we do it on the RL Gym side at Turing. So happy to answer any questions. We have few colleagues from Turing here as well. So if you would like to learn more about RL Gyms or model fine-tuning in general or human data, we are here to talk to you. Thank you.